Modular construction presents an attractive proposition, assembling a complete high-rise from finished volumetric rooms in a fraction of the time it takes to build on-site. This Gantt chart compares traditional construction timelines directly against off-site 3D volumetric methods. Because off-site manufacturing occurs simultaneously with site excavation and foundation work, total project schedules can compress by 20 to 50%. Yet for many early adopters, these massive time savings rarely translate to the expected 20% reduction in total costs. Instead, developers frequently incur what the industry calls a modular premium. Their overall project budgets inflate. The theoretical efficiencies of off-site building break down when the process encounters the real-world friction of a singular construction project. By definition, modular construction is the reallocation of labor. You are shifting unpredictable on-site work into controlled, off-site factory conditions. This diagram illustrates the three primary structural forms off-site manufacturing can take. Depending on the design, factories produce self-supporting load-bearing modules, core-supporting units, or frame-supported modules. Regardless of the type, every single block must be engineered to be individually stable. The widespread misconception is assuming these modules represent a new procurement method within standard real estate development. Profitability only becomes possible when developers stop treating buildings as isolated projects. Success requires the industry to manufacture buildings as standardized products. Realizing the financial promises of modular construction requires crossing specific mathematical volume thresholds and completely abandoning traditional architectural and engineering business models. This chart details cost variations. The primary benefit is a 10 to 25% drop in on-site labor. However, extra structural steel for transport raises material costs by 10 to 15%. Logistical penalties, like hauling and cranes, add another 2 to 10%. Ultimately, you are physically forcing massive volumetric rooms through tight urban and highway infrastructure, built primarily for passenger cars. On a small scale, the financial gains generated by pulling labor off the job site are completely consumed by the physical constraints of weatherproofing, transporting, and hoisting the modules. Overcoming those material and logistical penalties requires triggering deep economies of scale through factory automation. This S-curve shows off-site manufacturing's productivity impact. The first tipping point is 1,000 units per year, the exact volume necessary to justify the high capital expense of automation. Pushing past 5,000 units enables total process optimization, generating a further 5% productivity boost. The vast majority of local manufacturers in the North American market operate well below these numbers. They run on a project-to-project basis, constantly starting and stopping their production lines. A modular factory is economically viable only if it never stops running. Factory downtime is the exact mechanism that creates the modular premium. The primary bottleneck preventing continuous factory volume is the traditional design-build procurement model. It isolates architects from manufacturers during the crucial early design phase. This Venn diagram outlines the necessary alternative framework, Design for Manufacture and Assembly, or DFMA. Integrating DFMA with 4D building information modeling forces clash detection to happen digitally. Mechanical, electrical, and plumbing paths are fully coordinated before a single piece of steel is cut. Even with perfect digital coordination, manufacturers face severe financial friction. Traditional bank lending distributes funds sequentially based on physical, on-site construction milestones. This lending model starves modular factories. Manufacturers require massive front-loaded capital to purchase materials and build modules months before the destination site's foundation is poured. Shifting that risk and guaranteeing off-site cash flow requires integrated project delivery structures and specialized smart contracts, like those developed by Consensus Docs. You cannot finance and insure a continuous high-volume factory product using a fragmented site-based legal framework. Mature markets have already proven these volume and logistics barriers are solvable. In Sweden, prefabricated elements make up nearly 45% of multi-story buildings. In Japan, they account for 15% of single-family builds. The Swedish firm BoCloak, a joint venture between Skanska and IKEA, operates as a masterclass in treating housing as a standardized consumer product. To prevent visual monotony, companies like Lindbäcks employ an 80-20 rule. They use 80% standardized underlying chassis components, leaving 20% for customized architectural finishes. In Japan, Sekisui House achieves massive output, producing over 70,000 units a year, driven by government-backed industry alliances and extreme factory automation. Extreme logistical planning neutralizes the transport premium. Austria's Ho Vienna project perfectly optimized module shipments, requiring just 50 lorry trips for a massive high-rise build. These international examples prove that the structural engineering of modular housing is already solved. Operational success is entirely dictated by business and supply chain integration. Scaling modular housing across North America requires embracing 3 systemic changes. First, building codes must shift to performance-based standards, allowing manufacturers to innovate. Second, the industry needs front-loaded financing and standardized contracts to protect cash flow, guided by rigorous software integration. The technology to solve the housing crisis via high-speed off-site construction already exists. The true barrier is an outdated financial and legal ecosystem that must be re-engineered for the manufacturing age.